Thank you for attending this webinar sponsored by NEC Corporation. To learn more about the Programmable Flow Networking Suite featured in these use cases, please contact your NEC account rep today or go to NEC Corporation of America's website at www.necam.com/SDN.
To find additional SDN, OpenFlow, and network function virtualization resources, visit ipspace.net/SDN. Before going into individual use cases, I would like to spend a few minutes on real-life limitations we face with OpenFlow. Everything, as you know, works great in PowerPoint. A lot of things work great in labs, but when we get to production networks, what happens there? Will a particular implementation that uses OpenFlow survive large-scale production deployment? As always, it depends on the intricate implementation details, but it also depends on the architecture of the application, and I'll focus on the architectural aspects in the next few slides. First, do keep in mind that OpenFlow isn't something that would allow you to do wonderful things that were never possible in the past. Here's a quote from Professor Scott Shenker. He made that quote at the time when OpenFlow was launched, at the time of the biggest hype. He said, well, OpenFlow doesn't really let you do anything that you couldn't do on a network before. Whatever you can do with OpenFlow today, you could have done with policy-based routing in traditional gear. However, there are a number of advantages that OpenFlow brings to the table and the whole SDN concept. First, there might be some things that will be easier to implement with OpenFlow because now we can influence the device behavior at a more granular level. Second, there are some really hard problems that can be simplified if you have a centralized view of the network instead of partial views of individual network devices. Policies might be one of those problems, as well as traffic engineering, which is how Google used SDN in their network. But do keep in mind that the laws of physics haven't changed. We can still transmit only 1 billion bits in a second over a gigabit link, and the latency hasn't decreased because we have introduced OpenFlow. So whatever you can do with OpenFlow, there were ways of doing it with traditional tools in the past. Only some of those tools were clumsy or didn't work well or didn't scale well, and so on. As always, history is your best teacher. There were a number of technologies in the past that used either flow-based forwarding or cache-based switching, and this would be things like fast switching or multi-layer switching, or Epsilon had some flow-based switching. These things didn't work really well, so we figured out why they didn't work well. Second, there were a number of technologies that used centralized controllers, frame relay, SONET or SDH, ATM WAN, and so on and so on. All those technologies had problems if you lost the link between the controller and the network devices. And we had to implement out-of-band networks to control those devices, and so on and so on. Finally, things like InServe, the QoS where you would reserve bandwidth for individual flows, or ATM Lemon emulation, or ATM to the desktop, all those failed because it's impossible to scale the core devices to perform flow-based switching. Some vendors will tell you it's possible, and yes, some vendors have equipment that can make it work, but then you have to ask yourself, what's the cost of those boxes? Usually those boxes tend to be way more expensive than simpler boxes. Just compare a price of an ATM port to a price of an Ethernet port, and you'll figure out what the difference is. So, what were the lessons we've learned in the past? Lesson number 1, flow-based forwarding doesn't scale. Lesson number 2, path-based forwarding, like MPLS or MPI traffic engineering, is better than hop-by-hop forwarding, like running BGP on every internet router. And every time you have a central controller, you have a single failure domain, unless the controller is acting in an advisory role, where it sort of helps the devices do their job, but the devices can work independently if the controller fails. First question about SDN in general, and goes like, do you view the Cisco application infrastructure also as an SDN-based solution? It depends on how you define SDN. If you define SDN as an architecture where you have centralized controller with central view of the network, and that view of the network is used to program the network behavior, then yes, ACI is also an SDN-based solution, as are many other things out there. Second comment, SDN says that logically central controller, not just one controller. Totally agree with that sentiment. But do keep in mind that we are discussing OpenFlow-based solutions here, and with OpenFlow, you need the controller to control the devices. So yes, a confederation or federation of controllers makes a perfect sense, but one controller and associated devices is, at least in OpenFlow world, one failure domain. If you go into other technologies like BGP SDN that Microsoft is using, where the controller is just advising the devices what to do, then of course you don't have a single failure domain. If you take a look at Google's architecture, where they use OpenFlow only within the data center to control their WAN edge router, and then they use something else to implement traffic engineering. Yes, that is SDN, end-to-end, but OpenFlow is still within one data center because they consider that to be one failure domain. Let's see why we have problems with flow-based forwarding. There are two ways you can use OpenFlow today. One is proactive flow setup, the other one is reactive flow setup. What's the difference? Let's start with the proactive flow setup. It's like traditional routing, with the only difference that you can program whatever you wish in the switches. So let's say that we have the controller here and we have two endpoints A and B. Now, when the controller somehow discovers where A and B are, the controller would install forwarding entries, in our case, let's say pointing to B, and the event driving this installation of forwarding entries would be the discovery of B. So you discover the network topology first, then you discover the endpoints, and then you start installing the forwarding entries. So forwarding entries are installed based on topology changes or endpoint discovery, and not based on the individual flows. Now let's go to the other scenario. Let's say we are using a reactive flow setup mechanism. You don't install anything in advance, but when A sends a packet to B, because the first switch has no idea where B is, it sends a packet to the controller. Now the controller would look into the topology of the network and it would know where A and B are, and the controller would then send the packet straight to B, but it would also install a forwarding entry into the first switch pointing to B, into the second switch, third switch, fourth switch, and so on. Now, the other question also is, what is in the forwarding entry? Is it just a pointer to B, or is it a microflow from A to B? Why is this worse than the proactive flow setup? In theory, it should work. And there are controllers on the market today where the controller vendors claim they can set up millions of flows per second. With that, you would say, okay, that should be enough. The problems we have are in the physical switches that we use in today's network. So these limitations might go away in the future. I just haven't found a single switch that would work at the level where you could support per flow setup in a reasonably sized data center. The first question is the packet punting rate. How many packets per second, how many flow setups can a switch send to the controller? And this is purely the question of the switch CPU, as well as the question of the bandwidth between the forwarding fabric and the switch CPU. The second question is the flow modification rate. How many flows per second can a controller push down to the switches? Production switches today handle a few thousand flow modifications per second. You have to keep that in mind. So you cannot install a new forwarding entry for every session. That will just not work. And the third question is the flow granularity. Do I install a forwarding entry toward B, or is it from A to B, or is it from A to B on port 80? Yet again, switches on the market support from a few thousand to maybe 100,000 flow forwarding entries. If you only have a few thousand forwarding entries per switch, you obviously cannot install microflows like this. If you have 100,000 entries per switch, you may get away with that, but then you might get hit by the flow modification rate. Comment from Bob McCouch saying proactive sounds like the Plexi approach and reactive sounds like what I've always understood OpenFlow to be. You see, Bob, OpenFlow is just a tool. How you use that tool is a different story. The story that some vendors are telling you about OpenFlow is definitely on the reactive flow setup side, but that's just how they use the tool. You can use the tool in a totally different way in a proactive flow setup, which scales much better than the reactive one. Does the controller add an entry in every switch in the topology in a proactive flow setup? Thanks for that question. That's a great lead in for the next slide, but we'll get there. I have a few other questions before that. Another question, so the controller acts like fast switching in ASIC-based switches in reactive mode. Absolutely right. Regardless of whether you're doing proactive or reactive mode, in both cases, there are some packets that you have to punt to the controller. Those packets might be LACP or LLDP packets. Those packets might be unknown MAC addresses because you still have to do some discovery sometime. Those packets might be routing protocol packets. And the controller is working in exactly the same way as a CPU or slow path or fast switching or however you would like to call that is working in a regular switch or a router. Next question, how are the endpoints discovered? Usually, a controller, the whole OpenFlow network would implement a combination of layer 2 and layer 3. And if that's the case, then the layer 2 part of the forwarding topology would have to listen to unknown MAC addresses. So packets sent to unknown MAC addresses would be punted to the controller, and then the controller would install the forwarding entries. And likewise, ARP requests would have to be punted to the controller, and then the controller would send back an ARP reply if it has the ARP entry, or it would flag the ARP requests to all other switches that participate in the same layer 2 network. Yet again, this has to be done if you have to support a generic forwarding fabric. If, on the other hand, you support a limited environment like maybe OpenStack, where you know in advance what the IP and MAC addresses are, because you know where the VMs are connected, then you don't need to do any discovery. Question, can OpenFlow work in proactive mode too? Absolutely. As I said before, you can use OpenFlow either way. It's a tool. How you use the tool, it's up to you. Next one, so the discovery process is part of the standard? No. The OpenFlow standard specifies only how you install the forwarding entries into the switches and how the switches send the unknown packets to the controller. How the controller does the discovery depends on the controller. What happens if the controller loses connection with the switches? The existing forwarding entries remain in the switches, so the switches will continue to forward the packet, but the control plane is gone. So it's like a traditional switch. If the supervisor crashes, the data forwarding fabric continues to operate, but the switch cannot install any new information into the forwarding fabric. Is there some sort of broadcast store and filter to the controller? This is not part of the standard, but for example, NEC's switches do implement a mechanism to rate limit the packets sent to the controller. So yes, they do have something like control plane protection, but keep in mind this is vendor specific. A really good one is any OpenFlow controller using MPLS tags for endpoint routing. Are they aggregating endpoints like IP routers? And then subsequent, what I mean is use access switches as PE routers and core switches as P routers. By the way, another great intro to the next slide. Thank you. So what I'll be describing here is primarily what programmable flow is doing. And if you want to know more about the details of how programmable flow works, we did a whole webinar in February or so. It's publicly available, so you can download the videos either from YouTube or from my website and watch how programmable flow works and how it solves this particular details. So let's say we are working in proactive mode, so we forgot about reactive mode, and we can now do hop-by-hop forwarding like in traditional IP routing. So to go from A to B, I install the forwarding entry to B, pointing here and here and here and here. This one would go this way. So this would be hop-by-hop forwarding, identical to traditional IP routing. And like traditional IP routing, you have two problems. Problem number one is, let's say we don't have B here, but we have 10,000 Bs here. If you lose a link like this link here, you have to download 10,000 entries to this switch. And remember what we said before, a few thousand entries per second is the maximum flow update rate. So you would need several seconds for this switch to flip over and start using the other path for all destinations. Also, if we have something like this, then we have the same limitations regarding the autonomous response of the switches as loop-free alternate fast reroute in IP world. So if this link fails, for example, this switch cannot flip over to the other path because loop-free alternate path doesn't exist. This switch here might still send the packets back. Of course, once the controller downloads the new forwarding entries, you will get the new optimal topology, but that takes, as I said, a few seconds. So some controller vendors, in particular NEC with programmable flow, went down the path of path-based forwarding, which is really functionally identical to MPLS. In path-based forwarding, what you do is, once the controller discovers that it needs a path from A to B, it either sets up the path or maybe the paths are pre-signaled. So you have a path from the ingress switch to the egress switch. And then the controller would install a forwarding entry saying, well, send B down this path. Some vendors might use MPLS tags in their solutions. Other vendors might use some more creative solutions. I will not go into those details. Just remember that this is functionally equivalent to MPLS. Also, you could install a second path over here, and you can say this is now a backup path for B. If this link fails, then this first switch would immediately flip over to the backup path. But what if some other link fails? So what if this link fails? Now, if that link fails, you need a path going from this switch all the way over here. And when the link fails, you have to do path stitching here. And if you look at that, it's exactly like MPLS fast reroute, implemented with a slightly different control plane because everything is managed by the central controller. Like in MPLS world, why would you do this? Well, number one, to reduce the number of forwarding entries on these core switches. And number two, if you have paths, then it's easier to implement fast reroute. Yet again, a number of questions. I'm running MPLS currently in my campus. What benefit will I get by adding SDN? It depends on what solution you might want to use. If you're already running MPLS, then maybe adding some SDN functionality like automatic programming of something would help you reconfigure your network faster. Or when you start implementing a new campus network or when it's time to upgrade, you might consider an OpenFlow-based solution if things that I'll explain at the end of the webinar you'll find interesting. Next one, can I use multipath to increase bandwidth by using both paths? In theory, absolutely yes. In practice, I think most vendors support equal cost multipathing only. But there's nothing from the technology perspective that would stop you from using unequal cost multipathing. Also, do keep in mind that what we are discussing here are mostly data center, not WAN solutions. And in data center, you would usually build something like leaf and spine fabric, which has loads of equal cost multipath routes. Next question, is path-based forwarding based on group tables in OpenFlow? No, you have to use other mechanisms. Will you need hardware to support MPLS features to do path-based forwarding? As I said before, you don't actually need MPLS labels. There are other ways of doing that. But if you would want to use MPLS labels, then of course your switches must support MPLS-based forwarding. So you can't use all the goodies of a particular controller with all the switches that are out there. Some parts of what a controller vendor like NEC is doing just aren't part of the base OpenFlow standard yet. So they had to do their own extensions. Now that Programmable Flow supports OpenFlow 1.3, they can do all they need to do without the extensions, but on the other hand, there are not many OpenFlow 1.3 enabled switches out there. Really good question from Neil. If we had 1000 Bs, like in my previous example, would there be a flow entry per B, thus resulting in the same update problem? Well, you see, if I have 10,000 Bs over here, then I don't need 10,000 paths, so the core switches are okay. And on the edge switch, I can install 2 entries for B, obviously only if I have enough Tcam for 20,000 OpenFlow entries. And those entries would point this way and that way with different priority. So if the bottom link is okay, the traffic will flow over the bottom path. If the bottom link fails, the traffic automatically flips over to the top path without the controller being involved. So it's like prefix-independent convergence in traditional routing. And if something downstream fails, like this link here, then this core switch has to do path stitching. Is path-based forwarding an NEC-only approach, or is it covered under the OpenFlow specification? Yet again, remember, OpenFlow protocol specifies how you can download forwarding entries into the switches. How you implement forwarding with those entries and what the controller will send down to the switches is totally dependent on the quality of the controller. In NEC's case, I know that they do path-based forwarding, I'm not aware of any other OpenFlow controller doing something similar, and I have to admit I didn't look at OpenDaylight at all. So the last bit I have to add to this discussion, and then I'll go to the actual use cases. You can do, as I said before, a lot of things with OpenFlow. You can implement everything we ever did in our switches with OpenFlow if you wish. So you can do access lists, you can do QoS classification and remarking. Now the QoS features are becoming more and more included with the later OpenFlow standards, but you would probably need OpenFlow 1.3 or even 1.4 to get full QoS support. And of course, the usual stuff, the forwarding decisions. The problem is that these things are usually independent. So let's say we have C here as well. Packet coming from A would first go through ingress access control list, and then you would have a forwarding decision. So access control list would have maybe 10 entries saying permit or drop, and then the forwarding table would have entry for every destination. Now the problem we have with OpenFlow 1.0 is that we can only do one lookup. So we have to do the access control list and forwarding decision in one single lookup, which means that we have to repeat all the access control list entries for destination C and all the entries for destination B, and so on and so on. So if you have N entries in the ingress access control list and M entries in the QoS list and X destinations, you actually need N times M times X, approximately, entries in the Tcam. This will blow away your Tcam pretty quickly. Remember, some vendors only support a few thousand OpenFlow Tcam entries. So what we need is the ability to do multiple independent lookups. One for filtering, one for QoS, one for whatever, one for forwarding. OpenFlow 1.1 provides that with multiple lookup tables, so you can define steps in packet handling process through different lookup tables, and this will reduce the size of Tcam you need, so the switch resource utilization will be more optimal. But on the other hand, the problem is how well the switch vendors implement your intention expressed through OpenFlow tables and entries into their actual hardware. Obviously, this doesn't work in production at all. So every single vendor that offers a reasonably scalable solution, including NEC with programmable flow, had to do vendor-specific extensions when they were using OpenFlow 1.0. Now, with OpenFlow 1.3 being available on NEC switches, they can use multiple lookup tables that are available through standard configuration mechanisms. Question from Bob, going back to the previous slide. Does path-based forwarding really provide a scalability improvement in a large leaf spine design, where each spine is potentially in path for every pair of endpoints? It does. Think about it in MPLS terms. On the spine switches, you only forward entries from one leaf to another leaf. So on the spine switches, you need forwarding entries that go between leaves. On the leaf switches, you need forwarding entries for the actual endpoints. So yes, on the spine switches, you need orders of magnitude, lower number of forwarding entries than on the leaf switches. Is there still the idea or concept of running OpenFlow on production switches that are running standard spanning tree fabric path, QFabric, or IP routing, like ships in the night, with OpenFlow network as test, or just for traffic flows for better performance? People are talking about both scenarios. There are academics using OpenFlow on particular ports of a switch while leaving the rest of the switch for production use. And there are some interesting use cases, particularly in access control world, where you would use OpenFlow to implement packet filters and then send the packets that are matched by the filter through the regular packet forwarding mechanism. Next one, do switches with OpenFlow 1.1 or more generally support matching the same field multiple times across multiple tables? That's the idea. Now, whether a particular switch can do it or not, that is totally vendor-dependent decision, so you have to be very careful if you have a particular application in mind and talk with your vendor about what your particular vendor can do. Samarat, would you comment on what NEC switches can do?
NEC switches has multiple table implementations.
And you can match on, let's say, destination IP address in multiple times in multiple tables.
Yes, like you said, the actions are differentiated into different tables. For example, the MAC masking operation is in one table, and then the forwarding actions or, let's say, certain other specific operations are done through the other tables.
Oh, here's another one for you. How many switches can a typical controller manage?
Right now it is 200 switches.
Is that 200 OpenFlow or hybrid switches? And I think in your case, you are managing switches as pure OpenFlow switches, right?
Right.
Just from the scalability perspective, you have to keep in mind that what NEC is doing is actually the hardest thing to do, because they have to manage the topology changes in the whole network as well. So it's really easy to do an OpenFlow implementation where you just react to edge port changes and install access control lists, and then you dump the packets into regular processing. There you can scale to way higher numbers because you're not reacting to topology changes. You don't have any fast feedback loops. What NEC is doing is they're managing the whole network, including all topology changes, and that is way harder than just playing on the edge.
To learn more about the award-winning NEC Programmable Flow Networking Suite or the complete SDN ecosystem NEC is building with partners, and how you can customize these use cases for your own networking needs, call your NEC account rep today or go to NEC Corporation of America's website at www.necam.com/SDN. Thank you for your time and interest in NEC.
Additional SDN, OpenFlow, and network function virtualization webinars, recordings, and workshops, as well as other resources like books and case studies, are waiting for you at ipspace.net/SDN.